Welcome to our seminar series in the Gemini Center on Quantum Computing. Our speaker today is Joakim Bergli, and he has a PhD from the University of Oslo from 2002. He then was a postdoc in the University of Barcelona until 2003. And then he got a postdoc in the Princeton University until 2005. Which was followed by a postdoc period at the University of Oslo until 2009, where he became a associate professor, I think it's called in English, førsteamanuensis in Norwegian, and then he became a full professor in 2014. And today he will present some of his recent works, which is on synchronization in two-level quantum systems. So if you're ready, Joakim, you can take it from here.
Yes, so it's not perfectly quantum computing. It's more sort of basic quantum mechanics, but still it is quite clearly relevant because it concerns how a two-level quantum system, which we can call it a qubit, will be synchronized to some external signal. So this started like 3 years ago when there was a paper, this paper published, synchronizing the smallest possible systems, and there was even some sort of news story about this and the Physical Review webpage telling that you cannot synchronize qubits. And the claim in this paper was that two-level systems cannot synchronize, and three-level or more can. And I was a bit puzzled by this statement and curious to understand what it means. And then we had an exchange student who was here, we offer a special undergraduate research project, which is a special course that you can take. Mostly it's taken by exchange students that don't fit perfectly to our regular courses. So he asked to have this project, and we started to try to understand what was the reason why you can synchronize 3 or more levels and not 2. But before we can understand that, we have to understand what it means synchronize and in what sense this is meant. So let me try to explain you something what it means synchronization in classical dynamical systems, and this is something that goes back to Christian Huygens in 1665. The story is that he was sick and he was lying in his bed and watching he was constructing pendulum clocks. He wanted to have clocks that were accurate enough and stable enough to be taken on ships so that you can use them to measure time on board a ship, which you can use to measure your longitude, which was at that time a very central problem. So he had 2 clocks hanging close to each other, and he noticed that their pendulums would synchronize their motion so that they would go out and in synchrony. And he started to make experiments on that. And this drawing at the bottom apparently is his original drawing, and you can see his artistic talent is of the level of mine, so I didn't try to improve it. But this shows 2 pendulum clocks hanging from the same beam, which are suspended between two chairs. And then he noticed this effect that, and I think he understood at the end that somehow vibrations from one clock will be transmitted through this structure and transferred to the other clock, and these slight vibrations were enough to synchronize the pendulum of the second clock. I mean, it's not first or second, they synchronize mutually each other. And this, I think, was the state of the art for this science for many, many years. I wouldn't claim to be an expert on synchronization. I read one book, which is slightly, less than what you need to become an expert. But I read most parts of this book, which seems to be generally accepted as the proper reference for everything to do with this. And this, I didn't put it, it's published around 2000, I think. And it seems that it was a development in this community of nonlinear dynamical systems during the, let's say, from 1970 up till 2000, where they started to develop this more generally. And they apply it to many different things, not only physics, but there are a lot of biological or biophysical or examples or even medical examples of the rhythms of your heart or your breathing and your daily rhythms. And there is a lot of interesting things. So, I mean, if you want to read something which is not too difficult, I encourage you to look at this, because it's many interesting examples where they claim to find a kind of universal concept which lies behind all of it. And central to that is what is called self-sustained oscillators. And the paradigmatic example is exactly this pendulum clock that Huygens studied. So you have a pendulum that swings back and forth. But most importantly, you have, and this is what is contained in this term self-sustained, you have an energy supply. So you have this here, this weight that drives the mechanism, which means that it will not stop due to friction. It will not stop after. So it's not just a pendulum, it's a pendulum with energy supply. So it can, in principle, go on indefinitely. And I mean, these pictures are just taken from this book. And one of the points they stress is that there's a difference between these self-sustained oscillators and resonance, which the bottom figure here is to show what is resonance. And I don't know if it's clear what it means. I mean, there is a pendulum with a magnet, and there is an electromagnet with an oscillating signal. And if you put this oscillating signal close to this pendulum, you will induce oscillations. And this is what we call resonance. And what is the difference between this self-sustained oscillator, this clock, and the resonance phenomena is that, well, first of all, this resonant pendulum, it will stop if you don't supply this oscillating voltage. And you can think it's the same as, you know, this clock will stop as you don't supply the external force or the weight on this chain to make it work. But the difference is that this weight, this input energy here, doesn't have any frequency at all. I mean, it's something that is not oscillating. Whereas here, the external force is I mean, what imposes the oscillation from the first place. So one thing that they claim is the distinguishing feature is that this self-sustained oscillator, this clock, if you stop the pendulum for a slight time and release it again, it will not go back to its original phase. It will not be locked to the original phase. It will go back to swinging with more or less the same amplitude, but the phase will be different from what it would have been if you didn't perturb it. Whereas if you take this resonant pendulum and you stop it for some time and then release it, it will be out of synchronization with the external force, and then it will go back to that phase. And so it will always be phase locked to this external signal, whereas this will be free to have its own phase, and if you perturb it, it will come back to the stable oscillations, but the phase will be independent of any external thing. It depends only on the initial conditions. And this figure here is somehow to explain this concept. So this shows the phase space of some dynamical system, and there is this thick line which is a stable limit cycle for the dynamical motion, and you have trajectories of the system starting from outside, going in and being attracted to this limit cycle. You have trajectories starting from inside, going out, going to this, and this introduces the important idea that you should have some dissipation, some friction, and some gain, some energy source, in order to have a stable limit cycle. So this is what happens with this pendulum clock, that you have friction in the terms of internal friction and air resistance, which means that if I give the pendulum a bit of extra energy, it will have larger amplitude for some time, and then it will go back to its stable amplitude. If I break it a bit, the energy source will replenish this energy, and it will go back to the stable cycle, which is different from this also driven resonant pendulum, or if you take just a pendulum without any driving. I mean, it will just decay and stop, and it will not have any stable amplitude. So then they also distinguish between two two situations, what I call mutual synchronization and entrainment. So mutual synchronization is this situation which Huygens studied, that you have two pendulum clocks attached to the same support, so that the oscillations, vibrations from this one is transmitted through here and goes to affect this one, and conversely, this oscillations of this one goes to and affects that one. Whereas phase entrainment is something that looks very similar to resonance, in the sense that you have only one oscillating system, one clock, and you affect it by some periodic external force, and it will adjust its phase of motion to the phase of the external signal. And it is this latter situation that we studied. I mean, we only studied that. Well, I will come to it at the end. What about mutual synchronization? But so far, we only studied this thing. So, what are typical signatures of this synchronization? And as I tell, they managed to extract sort of general theoretical framework, which they could then apply to many different things, like biological systems. But it's simplest to think in terms of a simple oscillator like this pendulum clock, and it has there's an enormous amount of omegas in this thing. So I made a kind of table. Well, the last one is not omega; it is turned omega. So it's epsilon, but it's omega turned on the side. So everything is omega in some way. So omega 0 is the natural frequency of the oscillator that the oscillator will have by itself. Omega is the frequency of the external force. The capital omega is the frequency of the oscillator in response to the force. So omega 0 is the frequency without any external force. Then capital omega is the response frequency of this oscillator, the clock, when you have some external force, and the epsilon is the strength of the external force that you apply. And this left figure, it shows the difference between the response frequency, capital omega, and the imposed external frequency, small omega, as a function of the imposed frequency. And omega 0 is, I mean, it's written here, but it applies to this point exactly where this dashed line crosses the axis. This is omega 0. And what you see is that when you have omega, the imposed force, to have a frequency exactly like the natural frequency, is not surprised at the difference of the response, and then everything is omega 0. I mean, then this omega will be omega 0 at this point, and the response of the system will still also be at the same frequency. So it's not strange that you have the difference of this frequency 0 exactly when you are at the right frequency. But what you also see is that when you have an imposed frequency that is slightly different from the natural frequency, this will force the system to respond with a capital omega that is exactly the same as the imposed frequency. So you have a clock that has a frequency of one cycle per second. Then I put it on some support and I oscillate it with 1.01 oscillations per second. The pendulum of the clock will still go at 1.01 oscillations per second. It will lock to the external force. And this locking, it applies up until some mismatch of the frequencies at which it breaks down. At that point, the external force cannot anymore entrain the frequency of the oscillator, and it starts to go back to its natural frequency. And this is the meaning of this graph. And the middle figure, it shows the same thing, but for different strength of the external force. So, and here is the same plot as before on this axis, but then going kind of into the plane is the different or increasing strength of external force. It's clear that if the external force is 0, you will have no effect at all. So this region of synchronization, the width of this flat line is 0 here. But then as you increase the strength of the external force, you will make this region wider and wider. And this is what you see here, that this curve is having a flat region that gets wider and wider. And then if you plot it only in the omega epsilon plane, so the this plane here, you will see the shaded region is where you synchronize, and outside of that you don't synchronize. And
one quick question, since you wanted questions.
Yes.
If you go back one slide, yes, because on the middle figure I see sort of straight lines, but in the right figure I see not straight lines, let's say, quadratic or whatever.
What is kind of
hyperbolic?
This curves here.
Yeah, they're supposed to be straight lines, or is there some physics which makes them?
I think quite generally you can show that they are straight lines for small amplitude external force. So they will always start out as straight lines. But then when you go to larger amplitude, it will depend on the details of the system. So that they will deviate from straight lines. So I think this figure is more or less proper, that initially they look more or less straight, but then there can be some departure from that.
Okay, thank you.
But I think you can never have like a parabola starting here, for example. That you will never have. So you will always have two straight lines meeting, and they will have a finite but non-zero slope. So the slope here should be never zero. I mean, the slope of this line, if you take the derivative of this line and take the limit when you approach omega 0, it will be not zero and not infinite. Which somehow means that they are straight lines when you are very close to that point. But they can depart from that after some time. So then what about quantum systems? Yes?
Just maybe a stupid question. So it maybe I just read it wrong, but so for stronger external force, it should be easier to fit to the natural frequency.
For stronger external force, it is easier, or it's more, how to tell it? I mean, if you ask about this type of graph, is the stronger the external force, the more difference can you have between the natural frequency and the external frequency and still synchronize.
Yeah, I read it wrong. So you're synchronizing to the external force. That's why it's
Yes.
Yeah.
Yes. So that's why I mean this axis is capital omega, the response frequency, minus the external frequency. So when it is zero, it means that you are really synchronized to the external signal. And the width of this region depends on the strength of the force. And the stronger the external force, the wider will you have this region. So this force can then synchronize even if there is a larger mismatch in frequencies. It's very natural. It's not very strange at all. It's more or less obvious that the stronger force you apply, the more you are able to control the system. Okay. Then people started to try to apply this general idea to quantum systems, and there is a lot of literature about, not a lot, but there is a kind of considerable literature about it, and I'm not going to review in detail any of that. But I just put some questions that you can start to think about, and we will see if I answer them or not. So how can we transfer this idea? Because the idea in general was developed for classical systems, and there is a phase space, and you have dynamical system evolution on that phase space. And how do we do that when you come to quantum systems? Should we put Hilbert space as our space? Should we put the space of density matrices? How should we consider it? And at least one thing that we learned from these classical systems was that you needed gain and dissipation, which means that you have to describe an open quantum system, a system that is contact with some environment that can dissipate energy or give energy. And in general, you can describe this type of dynamics in many different ways. And well, I will come a bit back to it later, but I think you understand that in general, you cannot make a full description of the system itself when it is in contact with something else, because it starts to get entangled with the environment. Every time you have interaction between the system and some environment, it will be in some entangled state, which means that you cannot expect to have a full description in terms of the system itself. However, in many cases, you can have an approximate description. And this is what is given by this Lindblad equation. And I don't know, I didn't know how many of you are familiar with the Lindblad equation or not. I decided I'm not going to explain it in detail, but I tell you that it is an approximate equation that gives the time evolution of the density matrix of the system in presence of some environment. And it has a general form of time derivative being proportional to this commutator, which is what you get if you have an isolated system. But then you have additional terms, which are called Lindblad terms with these Lindblad operators L, which somehow describes the effect of the environment of the system. But note that it is only approximate. It can only be justified under certain assumptions. And also that it's an equation for the density matrix and not for the state, because you cannot anymore, since it is really entangled, it's in principle is really entangled with the environment, you cannot ascribe a well-defined quantum state, but you can describe a density matrix, the reduced density matrix of the system in this entangled state. And this is the equation that was used. So this is the same as the first slide somehow. So this was what they did. They used this Lindblad equation for small quantum systems, and this is how they arrived at this claim. Actually, I'm not going to explain that why they made this claim or why I don't think it is wrong. I will just explain you what we did with the two-level systems, and I think actually they are confusing some things that are not interesting to follow what they did wrong.
Joakim,
Yes.
sorry, can I interrupt? Can you maybe say what the claim is that they made? I mean, so I'm not really sure. Like, I understand what synchronization means, even, but like even in the simple qubit system, what's the claim so that they made? What does no synchronization mean in this context?
It means that that if you had a two-level system, and well, how to explain it without going into all the details what I did, I'm not sure.
Maybe we will come clear after.
No, I think it will be quite clear what we did, and you can ask whether this is synchronizing or not synchronizing, but I think what we did is quite clear. Maybe it's better to return to it a bit later, and you can ask the question again. So, well, I'm sorry it's a bit technical, this thing, but sometimes I think we need to write equations. So this is the model that we studied, and it's very simple. So it's a two-level quantum system. It has an Hamiltonian, which is just, well, it's diagonal. So it means that you have written it out in the basis of the eigenstates. And then you apply an external signal given by this Hamiltonian, which is just oscillating in or rotating in time. So actually, if you want to think about it as an electron with spin, it's an electron with spin in the presence of an external magnetic field pointing in the z direction and a rotating magnetic field in the xy plane. And I don't know how familiar you are with this magnetic resonance experiments, but this is somehow the really standard setup if you want to study magnetic resonance. So this is really nothing special with this model. This model was studied for many, many years. What is special, of course, is that you study this model in the presence of some environment. So you don't have only this system, but you have some external environment where you can take or give energy. And it means that the Lindblad equation will be of this form that I wrote before. The time derivative of this density matrix is the commutator of the Hamiltonian and the Lindblad terms. And I was even so lazy, I just copied from our paper, so the notation is a bit difficult to read, but there is this D is kind of what is called Lindblad superoperator. So D of sigma plus is that you take D and you put sigma plus in for this, and then you write out this of these terms. So D of sigma plus applied to rho is really this. So if you go back to the general Lindblad equation, I had sum over I, and here there are two terms, this term and this term. And the meaning of these terms is that you absorb some energy from the environment, increasing the state of the two-level system from the ground state to the excited state, or you emit energy to the environment, taking the excited state going to the ground state. Also, technically, it's very convenient to use a kind of rotating reference frame. So it is observed from an observer that rotates around with the same frequency as the external signal. And this is also very common in this magnetic resonance community. It's kind of the standard way to describe the response of magnetic, what's it called, nucleus with a magnetic moment in the presence of an oscillating or rotating magnetic field, is that you move to a reference frame that rotates at the frequency of the external signal. And the reason for that is that in this frame, the external signal will be constant. If you look at the rotating magnetic field in the presence of in a frame that is rotating with exactly the same frequency, the magnetic field will be constant. So you map this system to a constant in time Hamiltonian. And the effect of that is that instead of having this Hamiltonian, which is time dependent, you see here is the Hamiltonian. It's the commutator of the Hamiltonian with the density matrix. It will have some epsilon, which is a strength, multiplied by just sigma y. So the field is only pointing in the y direction. And also, instead of having, I see now that I changed from having h bar here to not having h bar here, but h bar is just set to 1 in this equation probably. Probably. No, it cancels. Okay, it's good. And then the outcome is that instead of having the full strength of the magnetic field in the z direction, you get just a difference in these frequencies. And this is because if you rotate at exactly the same frequency as the natural frequency, there will be dynamic phase factors that are completely cancelled by this. And then what we did, we studied stationary states of this system. So we take the time derivative of the matrix to be 0, and then to express it, I mean, the density matrix is a 2x2 Hermitian matrix with a trace which should be 1, and you can parameterize it by this what is called a block vector. And I thought that most of you knew what was the block vector, so I didn't explain it. So the density matrix is 1/2 times the density matrix plus block vector dotted with a matrix of polymatrices. And if you do that, you find the components of the block vector to be these terrible long formulas. And I mean, don't read them. It's not important. I think this is what is important. This figure, I think, somehow answers your question, Alexander. What is the meaning of synchronization? So, well, this and maybe one more later. I'm sorry you cannot read what can you read what is on the axis? It's very difficult on my screen. I mean, here is delta divided. I mean, it's delta in units of some gamma, but it's delta here and epsilon here. So it's exactly the same plot as what we showed for the classical system. You had the omega here, where delta is omega minus omega 0, so it's the same as this axis, and epsilon is the strength of the force on this axis. And what is shown here is the I don't know how to draw for you something, but you know the block vector. The block vector is a 3-dimensional vector and it describes the state of the system. I think I have a plot later. And maybe here. No, maybe not. Yes, maybe. Let's. I wrote on the dots, not vectors. So this is the block sphere. This is the state of the system in equilibrium when you don't have an external signal. And with an external signal, the state is moved. I mean, maybe I should have put block vectors, not just dots. I'm sorry. So the block vector is going from the center down to this dot. It's going from the center down to this dot. And then with an external signal, it is shifted to the right somehow. And then the block vector will have a set component, which is given by the thermal balance between gain and loss. And it will have an XY component, which is given by the response to the external signal. And what is shown here in this color coding is the length of this XY component, which gives you somehow the amount of how well it is, how much is affected by this external force. And well, for some special reason, this is the length divided by 8, but that we don't have to worry too much about, except that dividing by 8 explains why these numbers are so small. It's because you divided by 8, but there were some technical reasons why people started doing that.
Can I ask something? I'm not sure if I understand what you mean by synchronization, because what you did is just solving the Rabi model with some dissipation.
Yes.
And then you look for where you end up on average. So why is this, what's synchronizing with what? Of course, if you Rabi drive faster, then you will equilibrate, you will average out before you equilibrate, and the other way around.
Yes.
So what do we need to picture with the synchronization?
Wait a bit, and I will show you something.
Okay.
No, I mean, in some sense, you can tell why we started doing this at all, because this is what they did for the 3-level system.
Mm-hmm.
It's exactly, I mean, this student that did this project, he even copied their color coding and so on to show that our plots for 2-level systems are perfectly the same as their plot for 3-level systems. So in some sense, we just followed their path, and you can ask why they did what they did. And I think, as I said, I think they are making something which is not very clever at some point. So there's no reason to really.
Excuse me, Joakim, can I
Yes.
also interrupt? So
Yes.
what is the S of phi in the in that narrow strip that you, what is the maximized? Is it the
This is also something just taking from their paper about 3 and more levels. So it's something to map to them. But I mean, what I wrote on top, this 1/8 times the length of the XY part of the block vector is what is the same as this max of S of phi.
is it a sort of entropy?
No,
No. Okay.
absolutely not.
Okay.
S is what I call synchronization measure. And in this simple case, it is really the same as what I wrote on the top. So I didn't want to explain this S of phi because it was really not important for us. So that's why I wrote on top this length of the XY part of the block vector. This is what is the same as max S of phi. And it has absolutely nothing to do with entropy. So, so you're perfectly right. I mean, we solved this, what we call Rabi model, and you see that when you are close to resonance, you will have larger response of the system. When you're further away from resonance, you will have smaller response. And this is what is shown by this color plot. And the stronger the force, the more response you get, and the weaker the force, the less response you get. So it's nothing very puzzling at all. And you can compare it to this classical thing. You will see that it has somehow the same structure for the same reason somehow, but it's not sharp. It's not like a sharp region, but it's something diffuse. And then this is what I tried to also illustrate by these two figures, that you have, as you tell, the average state of the system is something here. And then the average state of the system, when you apply the signal, is shifted somehow. I mean, if you go back to the formulas I gave for the stationary state, you will see that it's shifted both in the XY plane and slightly in the Z direction also, but the Z shift is quadratic, and in the strength of the force, and the XY shift is linear. So at small forcing, you can think about it as just shifting in XY plane and not affecting the Z component. And then you can ask, what about not the average, but the system state itself? And this is what is illustrated by this blue by this blue curve. Is that okay? I can generate this average by some set of pure states along this circle with proper weighting. And I can think about it if I apply this external thing as this distribution of states on this circle being shifted by being more biased towards this side than toward that side. Of course, you can generate a given mixed or non-pure density matrix by many different ensembles of pure states. And let me wait with discussing that for a short moment. So what people said when they saw, and somehow to explain the difference between these two curves, the quantum picture and the classical picture, is that okay, there is also a theory of quantum, classical synchronization in the presence of noise. And then what happens if you add noise to the system is maybe not so difficult to understand. It is, I mean, here is the picture that we saw before. If you add noise to the system, meaning that you have some fluctuating forces in addition to your systematic periodic force, sometimes the state of the system will be pushed so far away from where it should be that it misses one period. So that, I mean, if you think about this pendulum clock, there is the external weak force that keeps it in track, but there is also a lot of wind blowing from different sides, and sometimes it goes, and sometimes it will miss a full period. It will not go back to being synchronized with the same phase. So, and the bottom figure is also taken from this book. It shows that without external forcing, you will have some more or less uniform distribution of phase. You don't belong to a particular phase. If you add some external force, you will narrow down this distribution of phases. If there was no noise, you would maybe have a perfectly delta functional spike here, telling that the phase is completely locked to the external signal. But with noise, you will have some broadened distribution. And it means that the response will not be perfectly, on average, equal to the imposed force, but you will get this kind of curve that the dotted, dashed one is what you get without noise. And then increasing the level of noise, you will have more and more smeared out synchronization. And this is what we would like to convert or to transfer to this picture from quantum mechanics. So we would like to have some uniform distribution along this circle, or maybe not circle. I mean, it could be region, it could be a strip on the surface of the Bloch sphere, which would be shifted so that the system spends more time or more larger probability to be in certain parts of this surface of Bloch sphere than the other. And this is what I would then mean by synchronizing this system, telling that the pure states that generate this mixed state are more likely to be in some places than in other places.
But okay, so that answered my question, I think. But I'm still not happy, because if you go back to your effective equation of motion in the rotating frame,
yes,
you could write down exactly the same equation with a static field, which I tune delta and E. It would give exactly the same equation of motion, assuming that the environment is still happy to absorb and emit energy at the qubit splitting. And you would get the same answer, you get the same dynamics, but there's no time dependence in your Hamiltonian. So what's synchronizing with what?
So you mean that this synchronizing...
You can go back to the slide where you showed the last equations. No, before. Yeah, so this one, d rho dt.
Yes.
If I put a spin in a field which is capital delta along z and epsilon along y, so tilted, and I would have an environment that's happy to absorb and emit energy, then I would write down exactly this equation. And then there's no omega, there's nothing locking to nothing, and I have exactly the same dynamics.
Yes.
So what's synchronizing to what in this model?
No, I don't know what you mean. I think the same could be told somehow to, I mean, if you go back to this book on classical synchronization that I refer to, they will also tell that, okay, if I have a pendulum clock, for example, or some oscillating system like that, which has a stable limit cycle, I can also define some sort of rotating or co-moving reference system. And they do that actually. They show how to do that in general, how to construct equal phase curves at different amplitudes, for example, that kind of corresponds to their dynamics. And then you can shift that problem to a static problem.
Okay, you can. So you're basically saying that the synchronization, when you say synchronization, you're just saying Rabi resonance.
Yes, so in some sense, I explain how this Rabi resonance phenomenon can be mapped to a description which is, analog to this classical synchronization pictures. Okay. And I mean, in some sense, that's what I think they failed to do in this paper, where they claim that you couldn't synchronize two-level systems.
I see.
They made a kind of unfortunate mapping in some sense that doesn't clarify the thing, and we show that you can actually make this mapping perfectly, telling that this typical quantum Rabi resonance phenomenon can be understood as a kind of instance of this synchronization phenomenon, if you like. But you can't forget about it. I mean, you can be happy with your old way of picturing the Rabi resonance, and we don't modify that in any way.
Just a small hint, Joakim. I think we've almost used up our time.
Yes, I know. I have only one more slide. So,
okay, perfect.
It will be just a summary, and that's the end. So what we thought, if we want to apply, this picture of a phase being more concentrated, or the probability of certain phases being more important than other phases, as a kind of way of explaining synchronization along this thing, we thought we wanted to apply what is called quantum trajectory theory. I don't know if any of you are familiar with it, but the general idea is just that you have a quantum system interacting with an environment. There will be entanglement. There will be some sort of entangled global state, meaning that information about the system itself doesn't have a well-defined state at all. But in some sense, you can think about it as information about the system being transferred to the environment. So if I have a system, it has certain dynamics. It will affect the environment in some way, and if you read out some property of the environment, it will contain some information about the system. And this trajectory theory is some way of taking into account this, telling that, okay, if I assume that I measure the state of the environment fully at all times, I will learn somehow as much as I can about the system without measuring the system directly. So I don't make any measurement of the system state. I don't affect the system state, but I kind of monitor all the information that leaks out from the system into the environment. And it means that you can take this average dynamic, which is described by the Lindblad equation, and what they call unravel it into a set of trajectories on the set of pure states, and there will be an evolution equation for that, which is stochastic because it depends on the measurement outcomes on the state of the environment. And then we have now a master student working on that. I hoped he would be able to give you some plots, so I could show plots of the probability density on the surface of the Bloch sphere under certain different conditions, but he was out with COVID the last week, so he was not able to finish that plot. I mean, he had it almost 2 weeks ago, but then he stopped. So at some later point, I can show you how this really is possible to follow, given that you know something about the interaction of the system and the environment. If you have certain special types of interaction, you will be able to find the probability distribution on the surface of the Bloch sphere. And I think that is time to stop.
Okay, thank you, Joakim.